So we are going to continue our detour into our, our engagement with linear transformation in the context of something called characterization of spectra. Characterization of spectra. Spectra, the way we have spectra, for example, in the physical sense, you can see there is a characteristic spectra. In the same way, the linear transformations have characteristic values which are reflected in their those spaces or those transformations. So that sense. There's an analogy between numbers and transformations. So these special class of transformations, if we have been a class of transformations which we have been studying, they are reflected by their spectrum. Now there are various theorems or results to that effect, which will go into a result which might be very interesting in this spectral analysis. So the theorem one, if we just on the book, says that if A is a self-adjoint transformation on an inner product space. So inner product space here. Inner product space, we had a discussion how we define that inner product space in a complex vector space. So where it's symmetric Hermitian. So that, and it will come positive definite. So the thing is that if it is inner product state, then every proper value of E, then every proper value of A. So it's also sort of solutions. A is real if A is positive or strictly positive or strictly. So the condition is more stricter, not only positive, it's mostly positive. Then every proper value of A is positive, and so or positive strictly, the way we have here. If it's positive and if it's strictly positive. So if the self-adjoint transformation, so it should be reflected there also. If A is a self-adjoint transformation, then every proper value of A is here, and then every proper value of A is positive. So it should be reflected if A is self in the original thing and in the self-adjoint thing. These things should be reflected. That the value of A as a characteristic solution should be positive in both cases, in this given case and in the spectral thing. So how we are going to prove it is that, so we ignore that the first assumption is a trivial case. For real case it may be trivial in the sense, but the job is more, challenges a bit more for the complex vector spaces, as we saw previously also. So we find vector spaces in terms of complex vector spaces. So we can have assertions. We can do the assertions for both real and complex vector cases. So in case Ax is equal to lambda x with x not equal to 0. So we can take it, so it's inner product Ax x and the modulus of it and inner product the modulus of it, sorry, the modulus of it is lambda. So it follows that Ax this is real. So if we just go to theorem 4 of theorem 4 of 71. If a necessary instruction condition that a linear transformation A on a unity space is Hermitian if Ax is real. So we have this is a theorem. A necessary condition for a linear transformation A on a unity Hermitian to be Hermitian is that that space Hermitian is that Ax is real for all x. So Ax is real for if it's Hermitian, Axx should be real for all x. This is a result we have previously shown as a part of a theorem, and you can just extend that understanding here also. Then so is lambda. If it's real Hermitian matrix and it is real, so it should be real for here also. And if Axx is positive or strictly positive, so is lambda. So this extends our understanding here. Now the theorem 2 says that if A is this theorem 5, and theorem 1, now theorem 2 says theorem 2 says that if A is a self-adjoint transformation, on a finite dimensional inner product space, then algebraic multiplicity of each proper value lambda naught of A is equal to its geometric multiplicity to the dimension of the subspace M for all solutions Ax is equal to lambda naught x. So again and again in the understanding of linear algebra, we have come to this thing that we not only have an algebraic understanding, we also have geometric way of geometric understanding to the or geometric visualization to the these vector spaces. So in 2 dimensions, it becomes more pronounced. But here the point to mention is that if the value in a finite dimension, the algebraic multiplicity of each proper value. So we not use proper eigenvalue, but proper value. If we have the solutions to it of lambda, they correspond to the geometrical multiplicity of the dimensions we are interested in, the solutions we are in. If it's 1, 2, 3, the map or correspondence is to the different dimensions to the things. And the proof can be in a very simple sense. So the proof is maybe I'll write it here. Proof is in a sense can say is that if n is invariant under adjoint transformations, and so is M perpendicular. That's the orthogonal space. And if we denote B and C as linear transformations as A. So previously, if you remember, C we have defined as A as B plus C or whatever that is. And so then what we are going to see. So in adjoint transformations, determinant of A is determinant B into determinant of C. This if you remember. Okay, if we have. So we are going to use this thing. So now if the eigenvalues is the proper value A minus lambda, it should be equivalent to determinants of B minus lambda minus determinant of C minus lambda. Since B is a self-adjoint transformation on finite dimensional space with only one proper value, maybe lambda naught. So it means lambda naught must have a proper value of B with algebraic multiplicity equal to the dimension n. What will be the dimension of this B? Now, so what we can say determinant of B minus lambda can be lambda naught minus lambda. So if you remember, the last time we had this lambda as a n solutions on the left hand side and the right hand side. There's a particular result. I don't remember exactly. So you can, for different dimensions, the different values of the proper value will be like this m for m dimensions. And C is and so lambda naught is not a proper value of C at all, and since determinant of C minus lambda is not equivalent to 0. So it's the result is proved in that sense, in the trivial sense. So what made the result work is that the invariance of m lambda, this space. So every characteristic root of this is corresponds to the every characteristic root of this characteristic equation of A is the proper value of the E. It's the proper value of the E. So that's it. So I'll just only state a very interesting result which follows from this and which you can see as a part of theorem 7, which says that if U is a unitary transformation, then on a finite dimensional space, finite dimensional, maybe that will be probably it's the finite dimensional unitary space. So unitary space includes this complex space also. Then the algebraic multiplicity of each proper value of U is equal to its geometric multiplicity, multiplicity. So maybe the value we get, the algebraic or proper value for U's may correspond to the geometric multiplicity in the dimensions which are associated with binary dimension vector space in which dimensions. So there is a algebraic and geometric correspondence which can be shown. Now we come to very important result in the linear this finite dimension vector spaces, and that result is called in the book called spectral theorem. In the words of the author, this is a very important result. A lot of related results are essentially dependent upon this result. So, one is the in the simple real cases we have a spectral theorem, but in complex cases we can also have spectral theorem, but we can the way we had a Gram-Schmidt orthogonalization procedure. In the same way, we have by method of triangulation processes, we can incidentally it can be made to follow from that how we do triangulations and how we solve matrices and other things. But if we want to have a in terms of theorem which will have some which will give essence of what this spectral theorem should mean is that to every self adjoint linear transformation A on a finite dimensional inner product space there correspond real numbers alpha 1, alpha 2, alpha r and perpendicular projections there R is strictly positive integer, not greater than the dimensions of the space involved. So that's the constraint, not greater than dimensions of the space. It should let the dimension. So every self-adjoint linear transformation A on a finite dimension inner product space, there corresponds real numbers and perpendicular projections. That's it. So there are real numbers for these self-adjoint transformations. They correspond to real numbers and perpendicular projections. So then first alpha j are pairwise distinct. So if it is that way, then alpha they are pairwise. This is one. The second is Ej is or pairwise orthogonal and different from 0. So this is an important thing. So they are pairwise. So not only they are orthogonal, but they are not 0. So previously orthogonality was attached with 0 in product space. So but they are pairwise orthogonal. So that's it. And the third is that Ej is 1 and fourth is so alpha j Ej, so it goes from j, so the index alpha j Ej is equal to adjoint A. So what's the way to show how to do it in that sense? So what we are going to do is Good here. So proof is proof. So if alpha 1, alpha are distinct proper values of A and Ej be the perpendicular projection on, but on what? On subspace. Consisting of all solutions such that this Ax is alpha Gx and J is also 1 to n. So condition 1 follows from that alphas are real, and they follow from if you go from the previous result 154, they follow from the theorem which we did yesterday. They follow from the theorem 4. Theorem 4 says if A is so. The thing is that these results can be shown by taking recourse to the previous class, the results we showed in the previous class. So one of the results was that if you have recollect the theorem 4, if A is a self-adjoint or isometric, then the proper vectors of A belong to distinct proper values or orthogonal. So this is, so if A is either self-adjoint or it's isometric, then proper values of A belong to distinct proper values. Belong to the distinct proper value. So the proper values belong to the case where they are orthogonal, and this should satisfy our first thing. Condition 1 is satisfied from this. It's this. If it's condition 1 is satisfied, this condition is satisfied. Condition 1. For condition 2 again. You go to theorem 4, which says, what is the theorem? Sorry, this is a condition. Theorem 1 says, sorry, I just forgot. So this is satisfied from, condition 2 is satisfied from this. If it's orthogonal, the A is, so I'll just go first for condition 2. If it's A is self-adjoint or isometric, then the proper vectors of A belonging to distinct proper values are orthogonal. So from this you can say it's orthogonal. So this is 2. From theorem 2 you can say it, this theorem. But for theorem 1, it's theorem 1. It says if A is and theorem 1 says that theorem 1 says that if A is a self-adjoint transform, this we just showed previously, on an inner space, then every proper value of A is there. If A is positive or strictly positive, then every proper value of A is positive or strictly positive. So we can add this. So we can have the first one. And the third one is Condition 2 follows from the theorem 4 and condition theorem 1. And if A and third one is if we infer that E is equal to E is equal to sigma j Ej, then E is perpendicular product projection. The dimension of the range of the E is sum of dimensions of range of Eij. So the dimensions of range E is the sum of dimensions range of E is consequently followed by 78. So maybe the theorem I just don't have one thing. So if you these results can be derived from our in the beginning of the class we just showed theorem 1, 2, and 3. For example, the theorem 1 says, so I'll just recap what the theorem 1, 2, and 3 says before we are going to just show it. So theorem 1 says every root of, so theorem 1 I have showed, theorem 2 maybe every root of a characteristic equation of self-adjoint matrix transformation of a finite dimensional Hilbert, finite dimensional inner product space is real. So that we have shown. The second was every proper value of isometry has absolute one. This I have also shown. Maybe every proper value of an isometry has absolute value 1. The theorem 4 says, this is theorem 1, 2, 4. 4 says that if A is either self-adjoint or isometric, then proper vectors of A are orthogonal. And theorem 5 says if a subspace is invariant under isometry V is invariant under isometry U on a finite dimensional Hilbert space, on a finite dimensional inner product space, so is M perpendicular. So the proof, we have shown it that the proof is if it's true for U inverse is equal to its self-adjoint, then this is this condition, and Y is equal to U inverse X, and you can have U star adjoint of adjoint will be the theorem, fifth case. So these 4, 5 results help us in trying to just properly how we can construct the proof of first, second, third, and fourth. Now we'll come to using those. First result I have not written. First result, maybe if A is a self-adjoint transformation, then every proper value of A is real. If A is positive, then the other is also strictly positive, which I have now using these 5 results, so we come to result 1, what it says that let alpha 1, alpha g be the distinct proper values of A and be the proper perpendicular projection of subspace consisting of all solutions Ax, these are the perpendicular solutions, perpendicular projection on that subspace consisting of all solutions such that Axg is equal to Axj. So condition this is satisfied from the theorem 1. Theorem 1 I have not written, maybe I'll write it here. Theorem 1 says that if A is a self-adjoint transformation, then what on an inner product space, then every proper value of A is real. Proper value of A is real. If A is positive or strictly positive, then it's also reflected in the on the other transformation also, which is also positive as well as strictly positive. So from this, so should it follow the this is pairwise distinct. Now it comes the, if it is pairwise distinct. If it is distinct or positive or strictly positive in one space, so it's also strictly positive in the subspace, orthogonal subspace. So from this A follows. The second is AG is pairwise orthogonal and zero. So you can see it from every self-adjoint transformation for inner product space is real, and so it's orthogonal, and it should be orthogonal. From this the third, say the result second is shown, and from result third follows from the condition. So from the orthogonality of the condition, I would infer that E is equal to, from orthogonality of the condition, we follow that E is equal to EJ. Then EJ is the perpendicular projection. And dimensions of E. So theorem 6 plus. So theorem 6 is follows from this, the range of this thing. To prove for this one, what we say is that take any vector x such that xj is equal to a times e of j of x, which means it's equivalent to axj. This means alpha j xj. This means alpha j ej x. So this proves the theorem, the spectral theorem. So the fourth follows from this. So if xj is a of aj, and where ej is what we have defined previously. Also ej are the perpendicular projections we have defined. So if xj is defined in terms of this adjoint of this perpendicular projection in this space, so you can say, you can write it alpha I is equal to this. So this completes the proof of the spectral theorem. And A is equal to this alpha j ej. These are the projections, these are the values, satisfied conditions 1 and theorem 3 of the theorem 1 in the spectral form A. So these are, so what if you identify with the book, the following the result, the spectrum theorem should basically it should we should follow an interesting. There are interesting follow-ups for the spectral theorem, which may be so. If it's also a part, it's also a theorem says that sigma j is equal to 1 to alpha j ej is the spectral form of adjoint transformation, self-adjoint transformation. Transformation A on a finite dimensional vector space, on a finite dimensional inner product space, then alphas are all distinct proper values of A. Moreover, if one is less than, this is less than or equal to k is less than or equal to r, then there exist polynomials with the coefficients p alpha k is 0 whenever j is not equal to k, and pk alpha k is 1. For every polynomial, pk is ek. So this result can be shown that, so if ek is a spectral form of self-adjoint transform A on a finite dimensional product space, alphas are all distinct proper values of A. So this is the thing. So if this is a spectral form, so we have an identified a self-adjoint transformation in a finite dimensional inner product space. And if alpha j, ij, these are the spectral form identified with these self-adjoint linear transformation for an inner product space, then alpha should be distinct. Should have a distinct. There should be distinct proper values. This is the thing we have to show, such that one is less than or k is less than, and so it should be always greater than one or less than that space which. So again, I just leave this proof for the reader. It's shown in the book in the sense, and maybe, or I just the proof is also very simple in the sense that so basically we are trying to show that if distinct proper values not only correspond to that space but also correspond to that spectral thing, the transformations which are linear transformations of a given space in the dual space or in the adjoint space. If there are proper values attached to this, so there should be proper values attached to the space which after that linear transformation, which may be in dual space or the space which has been linearly transformed, and it's an inner product space, to be precise, space sense. Such that if Ax is equal to I alpha I E I x is alpha j E j x alpha j x. So you can say that G G I I. So you can see it. You can repeat your index are there. So you can write it like that. So alpha j is the proper value of A. So now we have to show conversely alpha, it's also lambda is the proper value of A, such that Ax is equal to lambda x, and we write xj is equal to ejx. Ej is the projection in that subspace or dual space, in subspace, sorry, in that subspace. So if Ax is lambda x, is lambda times xj, and Ax A times alpha j xj, such that lambda minus so this is this, you subtract this from this, lambda minus alpha j xj is 0. So since x is pairwise orthogonal, so those among them that are not 0 are a linearly independent set. So from this you can follow that so if x is not equivalent to 0, x is not equivalent to 0, if x is not equivalent to 0, then what? This means xj is not equivalent to 0. So consequently lambda is equivalent to 1. So this means EI projections, EI EJ is 0 if I is not equivalent to 0, and EI EJ is equivalent to 1 if I is equivalent to j, or EJ square is equivalent to 1, or EI square is equivalent to 1. So from this, if you want to have A square as an adjoint transformation, product of A square is basically alpha j alpha G EG. Alpha G, it's a projective transformation alpha G or alpha I EI. We can use both. Then alpha G EG. If alpha I is equivalent to not equivalent to alpha J, then it's equivalent to 0. If alpha I is equivalent to alpha J, then it will be equivalent to alpha I alpha J, or you can see it will be alpha I alpha J EI EJ, or alpha, if it's I is equivalent to J, it's alpha J square EJ square. Now we come back to, if you remember, the thing that if we come to this result, I don't remember the result. Now we come to the result that this result. So you can have square, so it depends upon the dimension of this thing. So A n, the adjoint is basically alpha n j. This is the result. We have shown it using 3. Using 3. So from this, you can say PJA is proper value of this adjoint operator is this. So this is the result we had to prove. And to conclude the proof of this theorem, so it's equivalent to the dimension. So the characteristic value of this proper value of A should correspond to this orthogonal projection in that subspace modulo this thing alpha, and the value of alpha depends upon the value of J, the number of dimensions 1 2 3. So it's like this. Now the further I just it's an exercise that further we can write it as a representation in terms of J not equal to K T minus, we can write it like this. So it's an exercise you should attempt, can write for this satisfies the requisite properties which are part of this thing. Now what we are going to say is that this concludes our proof of this theorem, but we'll have a small detour into, I'll write it here, maybe I'll just explain it here. We'll have some definition, something called normal transformations. So it's again not to mention that the complex vector spaces become more important as compared to real vector spaces, and the complex vector spaces have those inner product spaces. Complex inner product spaces which are also called complex inner product spaces. Also called unitary spaces. So we'll mostly concentration on them. So if you remember also previously we also defined them. If the point is that, for example, if C can be defined in terms of A can be defined in terms of B and C, and there are two transformations, and we are going to diagonalize this and this. So we'll have addition of it or product of it. So the theorems, self-adjoint theorems, means determinant of A is equal to determinant of B on C. So So the thing is that so if we have separate operations of B and C, do the linear transformations still hold or not? You separately have linear transformation to this space and linear transformation to this space. So whether it will hold if we take linear transformations separately. If we take together, is one thing, or if we take them linear transform first on this, then on this, or linear transformations on B and B plus C together. So the thing is that it will not lead to the same thing because of the complex character of this. For real spaces it might hold, but for complex spaces, inner product spaces, these diagonalization procedure may not diagonalization procedure of arriving at those proper values, it may not necessarily hold to the same effect. And so we define a linear transformation normal. We define a linear transformation which is normal. Is a normal if it commutes with its adjoint. If it commutes with its adjoint, such that A dagger is equal to A dagger A. So this commuting property also, it's also not always true. It's not necessarily it will commute or things will not commute in linear transformations. So commuting linear transformations, it supports or satisfies commuting algebra. So there's a subtlety involved in this linear algebra or linear transformations. Whether two transformations can be linear transformations to support a commuting algebra or not. And for example, if A is a normal and we define A in terms of B plus iota C, and where B and C are Hermitian, B and C are Hermitian, and B we define as 1 by 2 A plus A star, the way we defined previously. Skew Hermitian and Hermitian, we just apply. We define this like this. Then B is equal to, you can check it yourself, BC is equal to CB. Then A is equal to B plus iota C and A star is B minus iota C. So from this you can say Hermitian and unitary transformations are equal or synonymous. So you can shoot from this exercise. It's a simple exercise, 2 lines, you can do it. So the class of transformations possessing a spectral form in this sense are called normal transformations. The normal transformations are those transformations which are Hermitian and unitary transformations in this sense. So half of the statement is easy to prove in the sense that if you go to the book, half of the statement means that if A is an adjoint, if you define A in terms of alpha j, Ej, and A star can be defined as alpha j, Ej star, such that A dagger may be equal to, you can see it here, such that E dagger A is A dagger can see it simply from this. So you can have Ej star, it's Ej square. So this is this thing. This is complex. That's fine. So now it's a bit of a challenge. So So you prove it, half of the statement is to prove it converse. The converse is you can start from the spectrality. If you assume spectrality, you should come to the original statement. You should come that its Hermitian and its unitary transformations. If you have a spectral transformation on the right hand side, you should conversely come back. So there is some problem. If you read the paragraph of the book, to prove the converse of this thing, means if a normal transformation can be defined this way, so it's Hermitian and unitary transformation. So it is simple. So if it has some spectral form is attached to it, from this spectral form can we arrive at the original thing, which is unitary and which is Hermitian matrix. So it's not an easy exercise. Why it's not easy? Is because of the fact that so maybe only the proof rests on just on valid for or so it's so we have assumed that this Hermitian it may be true for arbitrary transformations. This thing. So this thing may not be necessarily arbitrary. It's a general case. But for a particular case, we can define things in this way, and we arrive at this. But from this, can we arrive at this? If it's not a particular way of defining things, it's a general way of. If there are arbitrary transformations, so it's an open thing. So why he has the book is that we could have stated spectral theorem for normal transformation. The main reason we have traveled the present course was to, so we are, why the author is doing this, so he wants to motivate us to define as the normality. He has to define conditions of normality. So conditions of normality, there are two stricter theorems, which they are not that two. So theorem 1 says if A is normal, then necessary and sufficient condition that X is a proper value of A is that for A star, for X, A star, if A is the necessary, if A is X is equal to lambda X, then A star X is equal to lambda X. So what he is saying that the theorem says that if A is normal, then what necessary and sufficient condition that X is proper value of A, So this condition should be satisfied. So the proof is very simple, a two-line proof. You can have modulus of AX square we have arrived at this. So it can be written as the inner product of this, or we can write it like also this, A star A, X into X, or we can write it as, so we can change this A star X into X, or we can also write it as A star X into AX, A star X. So all of them will give us this product. And if A minus lambda is normal, so is A minus lambda star normal. So from this you can observe the relation A minus lambda is equal to A minus lambda star X. So we have arrived at this thing. So if this is defined, if A is normal and then these two conditions should be satisfied, which you can shoot from our this thing. The other theorem is that if A is a normal, then the proper vectors belong to distinct vectors are orthogonal. So if A is, so this theorem 2 says that if A is normal, then proper vectors that belong to distinct proper values or orthogonal. This means ax1 is lambda 1 x1, ax2 is lambda 2 x2.